120-degree phasing means opposing magnetic fields in space exist 2/3 of the time period being observed. So when we want to observe what our phasing results are going to be on our sensor coils over the poles, in order to obtain, well, first let's make this point here. The phase angle between two or more sources is not exclusively determined by the source, but also by the load it serves. Now, what we have here on the 666 machine, it's driven by an alternator, and we use megacable spirals because they have maximum mutual inductance, and we spiral each phase around each other in 3 components. Now what we do next is we reverse the polarity connections to every stack's middle coil. Then the magnetic fields will be in opposition 5/6 of the time period being observed. This causes the exterior poles on the stacks to be pushed outwards 5/6 of the time period being observed. So what we have is we have 6 interior magnetic compressions enabling 6 exterior magnetic expansions for a 6-phase effect. We therefore call this a 666 machine. Now, we can conclusively prove that a time distortion effect takes place on that, but we're not going to do that in this video. Everything's driven by an alternator at 465 Hertz, and it's pretty loud. We've tried to cover up the machine to reduce the sound, but we're going to rehearse what we're going to do here so that we can understand once we turn the machine on, we're going to progress through the chain of events. Here we have a schematic. We have inductors of some 2.4 Henry, I think it is, well, 2.6 Henry, around in there. It has 6,800 ohms reactance at this frequency of 465 Hertz. These are paired with capacities that have, by calculation, 50 nanofarad, approximately 6,850 ohms reactance, and we have switches on there. When we turn the machine on, the switches are going to be open, and we're going to observe what the coils generate without being resonated. And we got V1 for phase 1, V2 for phase 2, and VT for V total, which these are put in series. Now we're going to use then the law of cosines to determine the phase angle in several different case scenarios. We're going to demonstrate that there's a varying amount of phase angles, and these phase angles all depend on the load. Now first we're going to specify that as long as we're not drawing any current from these sensor coils, the polarity designations from the machine itself should be unaltered. But once we add secondary loads where it's drawing amperage, that will in fact alter the phase angle. And here we're going to see something pretty surprising, because when we turn this machine on, we're going to get approximately 21 and 22 and 20 volts on those 3 readings. And what we're going to figure by the law of cosines is that's about a little over a 60-degree phase angle. Now, what I've done a couple of days ago to demonstrate that there's something very wrong here with the way all these phase angles are adding up, we determine the phase angles by this method, is that, pardon the camera, I've got to get the page out here. Previously, we've demonstrated that when we looked at the other two phase angles, they were close to being correct. We had 117 degrees on the second test, 114 some on the third test, and again on that test we had 56 degrees, and it summed to 288 degrees in the circle, which is only 80% of what the observed time circle should be. But we're going to let that go now, and we're also going to demonstrate that this transformer has a third aspect. A third magnetic relationship exists, and that is between the secondaries themselves. These two high induction coils with voltage meters over them, and I don't like that glare, but we're going to have to deal with that. Find a spot where it's not glaring. That should be good. We're going ahead and turn the machine on, and we're going to engage each secondary separately. Now we can see here we have 23 volts in the front coil, 21 volts in the back, and 22 volts in between. Freaking glare. I don't know what to do about that glare. Okay, we're going to engage the back coil. We're going to turn the back coil on. And when we turn the back coil on, what we have on these coils also is a mega cable in between those primaries and the secondary. And we have a scoping of that. You're going to see that the voltage goes up and down. That's why when we look at some of these, that's at 10 milliseconds per division. This is due to a phasor effect, a rotating vector in time. We're not going to go into, but we're going to look at the scoping on each of these things. That is at 10 milliseconds at 0.5 volts per division. Now we'll go ahead and turn on phase number 1, phase number 2. I'm going to connect that. Wire. to 171 volts. We have 199 volts, and we have 25 volts. We haven't connected phase number 1. Watch what happens when phase 2's voltage will be decreased, and we'll see that on the scoping. We can see that on the scoping already. What's actually happening here is that just the 25 volts from the front coil is decreasing the amplitude of the magnetic field entering into phase number 2. Now we're going to connect phase number 1. Notice that phase number 2 decreased in voltage, and now we have 213 volts, 212 volts, 168 some in the back, and 367 between them. And our scoping shows now phase number 1 has considerably decreased phase number 2's magnetic field interacting with the coil. Every 24 cycles, it circles around. Now we're going to repeat the process that we just did oppositely. We've seen that it didn't decrease that voltage very much. Now we're going to see how that voltage will aid the front voltage. It is aiding the front voltage right now. Without that presence, here would be the voltage that we would receive. Notice that the back voltage has gone down to 174 volts, and the front voltage is in a reactive state, and we want to be able to see all 3 meters. I'm sorry about this production, folks, but notice the effect of the magnetic field again on phase 2. Now what we're going to do is go ahead, and we've shown that the secondaries themselves react with each other. And in that reaction with each other, they actually will create a back EMF so high that it repels the magnetic field from the primary entering it. Now we're going to end this video here. We're going to calculate the new phase angle rather quickly if we can. Looking at glare at that front meter. Son of a fuck. I still can't see it. This glare is going to be a real problem. I don't know how the video is going to come out. But we see that we got 173 volts in the front. And when we engage the back coil, it's going to increase that 40 volts and only slightly decrease this voltage. Now we're going to quickly show the phase angle here. In our second calculation, we'll take the inverse cosine of 212. Between them, we're going to divide that by twice the initial voltages. And then we have our new calculation, which shows that we're now procuring 149 degrees separation between them, undoubtedly due to the effect of interaction between those secondaries. So I think we've covered just about everything, and here again is the effect on phase 2. The magnetic field is entering that primary, is being completely overcome by the influence of the adjacent secondary. And we have, for reference, those are the three quantities that we're dealing with. And in a previous video, I've showed a neon being lit by the process, and it's only 12 degrees separation in time, and we'll include that as a flicker photograph on this video. And we haven't covered some of the stuff I wanted to, but we'll call this quits for now. There's no field being energized. We're only dealing with a 1 volt level to be achieving the somewhat phenomenal 367 volts. Thank you.